Welcome to Ask and Learn.
Okay, so we want to express a brute force algorithm that determines if there is a disjoint pair in these subsets. So I have this code right here, and you can look at it, but I'll kind of describe this code holistically. I'll describe what we're doing holistically, and then I'll describe the code as we go. So first thing that we'll do is we first assume that there is no disjoint OIN pairs. So we assume that there is no disjoint pairs, and as we run the code, we want to prove otherwise. So this whole code is proving that there is one disjoint pair. So the first thing that we do is we have S1, S2, and blah, blah, blah to Sn. So the first thing that we'll do is we'll compare is S1 disjoint to S2, is S1 disjoint to S3, all the way down to Sn. And suppose that none of these are disjoint. So we then have to go to S2, and we have to see if S2 is disjoint with S3, S4, blah, 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 all the way to Sn. So now it's important that we don't actually compare to S1 because we don't compare to S1 here because we've already compared S2 to S1 here already. And you have to do the same thing for S4, compare to S5 and blah, 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 all the way to Sn. Then we compare Sn minus 1 to Sn. This is our last one. So that's what this first for loop does. This line here, that's what this line does. This first line loops through S1, S2, S4 to Sn. Well, this is S3, sorry. S3 is 4. So that's from 1 to n minus 1. And the second line of code goes from S2, S3 to Sn, S3, S4 to Sn, and so on. So now this line of code, what this code does is that it compares S1 and Sn. So sorry, it compares two sets Si and Sj. So it compares if these two are disjoint or not. Now to see if they are disjoint, we do something completely opposite. So isolating S1 and S2, what we do is assume that they are disjoint. Disjoint, and prove that they are otherwise, and prove otherwise. So to prove otherwise, what we know is that the set Si contains numbers in the range of 1, 2, 3, blah, 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 to Sn. So what we do is, if we can find one number of all of these n that is in both of these two sets, then that means they are not disjoint. So that's exactly what this line of code does here. So it takes two sets Si and Sj and sees if K is in Si and Sj. So if K is in both sets, then it is not disjoint. So here we assume that they are not disjoint. We assume that they are disjoint. So are disjoint, Isjoint, and we prove otherwise. So if we have been able to prove otherwise, so then that means Si and Sj are not disjoint, and we have to do another. We have to compare different sets. If they are disjoint, so that means if they are disjoint, then that means this will never be true. So this never ever reaches. So then disjoint would be true, and then answer would be true, and so we return the answer. So now we want to give a big O estimate for the number of times the algorithm needs to determine whether an integer is in one of the subsets. So, or really the cost of this computation. So I'll do this in blue, maybe. Yeah. So here we perform one computation because, or really we do two computations because we compare if K is in Si and Sj. So we do two computations here. We do this computation n times. So all of this thing would be 2 times n, and then I'll use green. So then here we do this whole thing n minus by 1 times at the worst case. So we can just really consider that as being n. So we consider n minus by 1 to be close enough to n. So this is 2n squared, and this whole thing finally we do this n minus 1 time, which is close enough to n. This is 2n cubed. So the order is 2n cubed which we just dropped a constant, so that's just n cubed.